Hello and welcome to day 6 of the How to Get Started with Solana Development in 2026 video series. Today we're gonna once again build our own program, but this time not with Anchor, but with Pinocchio. And we're doing this because I want you to understand one more essential thing, and that is serialization and deserialization of data, specifically account data. Because so far, Anchor has taken a lot of the difficulty away from us, but I want you to understand how it works under the hood, such that you really understand what's happening. Because that's a dev's job, to know what you're doing, to know what's happening. I mean, of course you can go through your life without understanding all of the things, and keep relying on the frameworks to take care of that for you, or the AIs to fix that. I'm not your grandma, I'm not telling you what to do. But I'm just suggesting that having an understanding of what serialization is and how it's used in the context of Solana development is really helpful for writing your own programs correctly and efficiently. Not saying you can't get around it, just saying that it's helpful. That's why I put it into this video series, because on other systems it might not be that prominent, but on Solana it really is essential. That's one of the tasks of a Solana developer, is to come up with how data is being stored, in what form. Because really underlying, it's all just bytes. So we, as the devs, are responsible for serialization and deserialization. So let's get started with day 6, how we really write accounts. Subtitle, it's all just bytes. Okay, let's get started. Yesterday we were talking about tokens and we were getting codecs here already. We're gonna talk about codecs in a second a bit more. Codecs are gonna be relevant for today's video because codecs is how we do the serialization and deserialization with the Solana kit. But I wanna get started with writing a Pinocchio program. So what I'm gonna do is I will cargo init. So I'll basically just create a Rust program. Specifically, I want a library. Oops, now day 6 is my entire Rust thing. Well, sure, why not? Let's call it day 6. Because this doesn't create a new project folder for me. It just takes what it has here. That's fine. And in the source, we have the lib. Again, this is pure Rust. We want to make it Solana. So I'm gonna cargo add Pinocchio. This is basically a library that just has a few dependencies like Solana address, Solana program error, some of the Solana crates. Pinocchio used to not have any dependencies, and now it has a few because it uses the same types as the Solana SDK. And Pinocchio itself is like the Solana SDK. If you write native programs in Solana, you would use the Solana SDK. Pinocchio is just a little more efficient. That's why I enjoy writing with this one. So might as well teach you that, since it's not that much different, but it doesn't give you such a nice template. So the way I like to go about this is I like to copy the entry point code from here. That's just the GitHub, and put that in there. And that, if you want to use Solana program log, we can cargo add that. But this one has a bunch of dependencies. And again, I don't try to write an efficient program today. I'm just saying that Pinocchio is your go-to SDK if you want to write compute efficient programs. What that really is also out of the scope of this video. Watch some on the compute budget program that I did. Today I just want to use it to understand serialization. Okay, now this is already a working program. We could already compile this. We could say cargo build SBF. That, by the way, also comes with the Solana CLI when we installed that, and then it will build all the dependencies first, and then our day 6 program. Great, just have 3 warnings. And that did a similar thing that the Anchor build does. It creates this target. Oops, another thing, if you're writing Solana programs, I keep forgetting how that is done, so I always need to look it up. Here, we need to set the crate type. There we go. You just gotta copy that in. And then if you build, then it actually creates this deploy binary here. So that's an ELF file. Same as we had with Anchor, just this time it's a bit smaller. And to deploy this, I don't say Anchor deploy. I need to go through the Solana CLI. I would need to say Solana program deploy and then give the path to this target day6.so, and like that I could deploy this. There we go. My program ID is ECQ because that's that key pair here. I could provide a different key pair and have a different program ID, but for us that's fine here today. And then I could directly call this program by putting it in here, creating an instruction to our program, and then sending it through the RPC. It's the same script as we had before. And here we go. That would be a transaction on our program that we just deployed. Here it doesn't know what the program is because we're not uploading any IDLs, but it says hello from my Pinocchio program, which is exactly what our program is doing. That's all it does. And then it says OK. So same thing, the OK makes the instruction return with success, and that makes the entire transaction be successful. And that's it so far. Wow, it now has size in bytes. The Explorer is changing with every day. Now, before we make any progress with our program, I want to explain to you what I mean with serialization and deserialization. Because that happens everywhere, just that you might not be super aware of it. For instance, it does happen when we send our transaction. The send and confirm transaction, what this thing does before it actually sends the transaction, because here we have basically an object with the transaction message and the signatures, and the transaction message contains the instructions and the block hash, and all of that is being sent to an RPC. Now, obviously, it's not sent in that format. It's being somehow converted first. And the kit does those conversions with codecs, in this case, a transaction codec. A codec always has a decode and an encode function. The encode function always takes the high-level object, in our case the signed transaction, and it will return bytes in the form of a uint8 array. So we have a read-only uint8 array here. I'll call this the transaction bytes maybe. Or in other words, the serialized transaction. Because what that does, it takes the infos of the transaction and it has a certain order of where it puts stuff. But maybe let's start a bit simpler and encode something else. Let's encode a string. So the serialized string, we use a UTF-8 codec. We can encode a string hello. Let's do 78 with 3 exclamation marks. And then let's do something even more simple, number bytes, and get a U64 codec and encode a number. I could do a big number. Maybe let's do a classic computer science number, 1024, and I will log the string bytes and I will log the number bytes. So the serialized string and the serialized number. Let's just look at that, because that looks as follows. The string is 8 bytes in length because I have a 8 character string, and here we see the 72 because that's the ASCII characters. It takes one character, converts it to a number, and that it does for all 8 characters. We see the double L must be here and the 3 exclamation marks must be those. And if we look at the number, that's a lot of zeros and a 4 here. Why? Because I chose that specific number, which is a power of 2. So that's 2 to the power of 10. So basically what we're having here is one number that's made up of 8 bytes. That's a so-called U64, 64 bits. First 8 bits are here, the next one here. So here is 2 to the power of 0. Here is 2 to the power of 8, 2 to the power of 16, and so on. So if we have a 4 here, then we have a 4 times 2 to the power of 8, which is the same as 2 to the power of 10. And that's why this represents this number. And here comes in the interesting part. Looking at those two integer arrays, I can make a guess what they represent, but I cannot be sure. For instance, this here could also just be a very large number. And there's no one who can stop me from saying, hey, my number is, I'm getting this codec again, and I decode, now that's the other way, that takes the bytes and returns the high-level representation. And I could just decode the string bytes to a number. That would be a very freaking big number, this one, but we could interpret this as a number. Same way as we could interpret this as a string. It would just not represent much because it's a lot of null characters. So if I would take the number bytes and I would decode those, then obviously I should get back the same number that I put in. Okay, now that's for simple things, just one string or one number. Now let's say I wanted to put both the string and the number into one single byte array. How would I do that? Well, I would need to define which one comes first. And usually a good practice is to have the ones with fixed length first. That would be my number here. So I would create a struct codec. And don't worry, here it gets a bit complicated. I don't want you to be able to reproduce this, just follow along for now. Here we put in an array of, and I can name them as I want. I'll name the first thing number, and it's gonna be this codec, and the second thing I call it the string, and that's gonna be a UTF-8 codec. Okay, so how do I use this thing now? Forget about that part. Let's call it serialized bytes, because we serialize both the number and the string. We call the encode, and we put the number, this, and the string, this. And that just represents those things that I put in the struct here. And then if I print that, this now results in a 16-byte array where the first 8 bytes are my number and then directly afterwards the string. And what I did here is I serialized a number and the string. Serializing just meaning put them in a series. First the number, then the string in this case. And I define the order of this. I could say, nah, do the string first, then the number. Then it would look different. Then it would be first the string, then the number. But there we might already see an issue. We don't know how long the string is. We can define that it always must be exactly 8 characters long, or we could, for instance, add a codec size prefix and say my maximum is 255, so I just get a U8 codec here for encoding the length. Then I would add one more byte that says how long is the upcoming string, 8 bytes in this case, so that's the 8 bytes representing the string. Then comes my number. But now my total grew to 17 bytes. And see, all of that, making those decisions, is our jobs as developers. It's always a question of how is the data serialized and then also deserialized. Because this thing, I could go the other way around. I'm gonna store that codec, struct codec, and then I can deserialize my data with the same codec using the decode, and I put in the serialized bytes, and then I should get out the same thing I put in. Let's check. There you go. Then we're getting out the same thing that we put in. From that data, we deserialized that data into this representation. That's what I mean with serialization and deserialization. Okay, so far so good. Coming back to my transaction, the transaction codec is nothing else than a more complex example of what we had here, just that here we need to encode all of the accounts, all of the instructions, what's the block hash, what type of transaction it is, and all of the signatures. So we have a bunch of things to encode, but there is one standard way of how a transaction is supposed to be serialized, such that the RPC then also understands that data. Because those bytes, we will then put them in base 64, such that we can put it in HTTP, such that we can send it. But that's essentially what the RPC will get from us, not this high-level object here. So if you also want to have a look at this, we can print the transaction bytes for fun. Those are the individual bytes. And I did make specific videos on transaction serialization where we go into more detail. Just real quick for you, this might be just random data. For me, having worked with Solana a bunch, I see, okay, this transaction has one signature. That's the signature. It has one signing account, 0 writable accounts, and one read-only account. That's the program, that's the fee payer, and so on. And that's also the same thing that we would get if we get a base64 encoded wire transaction for this signed transaction. Just that here we're actually getting base64. There we go. So that's the base64 string then of those bytes. And that is something that I could put into the inspector here, and then it will deserialize the transaction again and show me all of the accounts. This is the fee payer, those are the other accounts, and that's the instruction. And here I could also simulate that, and then I see what would be happening if we were to actually send that transaction. So yeah, that's a serialized transaction. Just to point out that this happens in a lot of places where we have the object that we work with in code, but then it's put into just some bytes. And from those bytes, that could mean anything, but if we know that it's a transaction, then we can associate the bytes correctly and be like, oh, that one means that there's one signature. Oh, that one means that there's one writable signer, and so on. Okay, good enough. I think you understand what I mean with serialization. Let's come back to the actual program. Because also here, we find ourselves using serialization or deserialization in that case in the program. The program already deserializes the input for us. That entry point macro does that for us. Because the program ID, the accounts, and the instruction data is also just provided as one long piece of just bytes to the program, but those bytes come in a specific order, and so we can deserialize it, and then we get the instruction data, accounts, and program ID. If you're interested in the details, also I made a video on the entry point. You can look that up, but here we can just take that for granted. That's how this data comes in. However, we will once again need to deserialize it further when we are working with instruction data. And here, for the first time, we can finally decide how that's supposed to look. Because with a transaction and with the entry point, that's already defined by the Solana specification, or with the entry points case, the loader program's specification. But with the instruction data, here all of a sudden we are in control. Because remember, with our Anchor program, Anchor did that for us, that we just implement instructions and then Anchor knows how they are called. Not with Pinocchio. With Pinocchio, we will need to implement that ourselves. We just get the raw instruction data as a slice of bytes. So if we want to have different instructions, we will need to work with this instruction data. So for instance, I could match the first byte of the instruction data to be my instruction discriminator, for instance, and I could say if it's 1, then execute init instruction, for instance. And if it's 2, set the mood. And if it's 3, get the mood. And if it's anything else than that, we say invalid instruction data. This could be how I map my instructions manually, because what I get as instruction data, I define that. I, as the developer, can say, that's how I interpret the instruction data, because I'm responsible how that is serialized and deserialized. So that's the one way. Let me quickly build that and deploy that, because then we will see when we call it, our instruction, if we just call it like this, if I just do this, then I will now get a panic. Oh yeah, I will get a panic because I'm not providing any instruction data, but my implementation uses the first byte, so we panic. So maybe as a good dev, I should do something like check that the length of my instruction data is at least what I expect. And if it isn't, then also return that error. Then redeploy that real quick. Wrong way around. That happens to me a lot. Sorry, fixed it. Okay, now, then I'm getting this invalid instruction data error from here. Or also because I will need to provide data here. And again, I as the developer say how this data is interpreted, which means what I put in here must reflect that. The first byte here is my instruction discriminator. So for instance, if I want the initialize instruction, I need to put a 1. Then my program would run the init instruction. If I put something invalid like the 0, then I will once again get the invalid instruction data, because I am now manually mapping that, because I said that the first byte of instruction data represents my instruction discriminator, and that decides what real instruction is being called. And here we see that in reality, a program just has one execution path. It can just take the input that it takes, the instruction data, to then behave differently. That's what we then mean with it's a different instruction. But really, as we discussed on day 2, an instruction really is just this program is being called with this instruction data and those accounts, and then it's doing some execution logic. But for us as devs, if we want a program to have different instructions, then we need to define that through the instruction data. For instance, with just 1 byte, or Anchor uses 8 bytes of the instruction discriminator. For most cases, it's good enough to have just 1 byte. So that's how we would do that. That's how we could distinguish between different instructions, if we want one program to do different things, which usually you want to. Okay, let's go a step further and actually work with accounts as well here. We're gonna build a similar program that we did on day 3 with this set mood and get mood, and we're using a mood account. And let's start with the most difficult thing, the initialize. Actually, I think to keep it simple, I'm gonna skip the initialize for now and not work with PDAs. We will go there later, but I want to stay with the account serialization first. So we just create the account with the system program as a separate instruction, as we also did in the first iteration of our Anchor program. So let's go with a set mood instruction, and I'm gonna just copy this process set mood. They're gonna be my implementations for, well, I don't really need the program ID. I don't even need it here. And here I'm just gonna call the process set mood with accounts and instruction data, and here process get mood, and we'll get to the initialize later. Now for the implementation, let's get the accounts. Also that I need to define in which order they come in, like I did here. I had the state and the authority, so the mood account and the authority. I'm gonna do the same thing again, but maybe I want to do one more time a guard of accounts. I'll do invalid argument. If you don't know which error you should use, I made a video on those. Invalid argument is for the accounts if they're invalid, or actually there's one even better one. There's a not enough account keys. That's the even better error in this case, because we're expecting 2 accounts, and then I'll save them. My mood account is the first one, and my authority account the second one. And since I haven't even initialized that account, let's not even work with the authority account yet. Let's just do the mood account, because now we need to define what is stored in that mood account. Similar to how we did it here, we say, oh, first is this, then is this. Just that Anchor also did the type of account for us, which we might want to do as well, like a account discriminator. But for this to make sense, I think I will need to initialize it as well. I'm gonna do the separate initialize, even if the initialize doesn't create the account, but it initializes the account. Otherwise, this does not make sense. Okay, I'll also do a process initialize. And then we gotta say how that account looks like, because otherwise it is just data. The data of the account is always just a bunch of bytes. So we get to define what those bytes mean. For instance, I'm just gonna call it mood account here. I say there will be a discriminator, and I'm just gonna do a U8. Anchor does 8 bytes. I'm just doing 1. Then I will store the mood as the U8. And then, while I'm here, I think I might as well add the authority as well. Yeah, that would do the same thing as with the other one. And this one, I'm gonna do differently though, just so you see something else. I'm gonna do an option for an address. So there can be an authority, but there doesn't have to be. Just so you see how that is serialized. Okay, now how do we use this? For now, there's just a struct. Now, to use this struct, actually, hold on. Before, let's do it this super ugly way, just so you understand why we do the things that we do. We could say something like, okay, mood account, we get the data, and to initialize, we write to the discriminator. So we write to data 0, let's say this 0 is uninitialized and 1 means it's a mood account. This byte here I use to tell me what type of account it is. Compare token program having token accounts and token mints. Those are two different types. They don't use a discriminator, they do it with the account length. Token extensions then had to manually add that. But anyway, so for us, I want to write a 1 to identify my mood account. So I write data 0 is 1. And then the mood, I will let that stay at 0 because we will set that later. And the authority could be like data 1 to 6 to 6 plus 32. Guess I gotta try borrow this instead, not work with the pointer. Then I can copy from slice. Now I threw away the authority. No, give me the authority back. I want the authority account as well. So from the authority account address, 2 bytes maybe. Yeah, that looks like it compiles. Okay, so we borrow the data mutably. Then we manually write the first byte. So that's writing it into here. And then we manually write the address in the authority. And I will also need to manually write a 1 here to say for the option it's present. That all looks a bit ugly, but it should work. Let's test this. Okay, now we will call our program and we need to manually add the create account instruction for a new account. We just generate a new one. We add it to our program. We pay for it, space. Now this one is interesting because again, we need to know how much all of that is gonna be. So we need to understand how all of the individual parts are serialized. That's 1 byte, that's gonna be serialized as 1 byte, same here. How is the option serialized? Well, that's the good question. The address is 32 bytes, we know that. But the option, we again have several possibilities how we can serialize it. Depending what library you use, it might take 4 bytes to say whether the option is present or not, or maybe just 1 byte to say whether the option is present or not. Ideally, it would use 1, it could use 4, just to be on the safe side, because I don't know how I'm gonna do it yet. I will calculate with 4, so I will have 32, although that might be a C option and not an option. But whatever, 32, 36, 7, 8. Let's go with 38, just so we're on the safe side. And then Lampert's. We get minimum balance for rent exemption for 38. That's the create account instruction. We gotta do that before our instruction in the transaction. And then we say call the initialize. So we put the 1 here and we need to provide the correct accounts as well. So accounts, you will get first the new account. So that's gonna be my mood account with role writable. And the second one is the authority, which is going to be my key pair with role signer. Okay, let's try and call our program. Cool, that even worked. We created this new account and the initialize instruction was executed with success. So let's see if that account was actually written to. Yep, that looks good. That did what I expected it to do. I wrote the 1 for the discriminator. The mood is still 0. I said yes, an option is present, and then I wrote the authority into here as well. That's what I did with this code. Nice. However, that's still a bit ugly, but I hope you're getting the idea of serialization. You as the developer are responsible how the bytes of the account are being used. The bytes of the account is just a bunch of bytes. And what you make of them is your thing. You gotta decide that. You need to say how it's being serialized and then deserialized. So we defined, hey, the discriminator, that's the first byte here. This one is the option. And then this one is the authority. We wrote that at this location here because I said 4 bytes is for the option. Now, this is still ugly. Why is this ugly? Well, because we're working with those numbers directly, and it's like, I do have this struct that neatly says what it is, but I'm not really using this struct. I'm just referencing it kind of like by eye, but that's not nice code. So I could use a serialization library, and the most well-known one is Borscht. By far not the best one, and I will make videos on better and faster ones, but we did use it in Anchor, and it is used in other Anchor programs. So for this basic tutorial, let's just use it. So we wanted to be able to serialize and deserialize this struct. So I gotta somehow import that stuff. So I say cargo add Borscht. There we go. Then we should be able to import this, and address then doesn't have Borscht serialize. Okay, maybe I don't want to use Borscht then. Since Borscht doesn't support address, I think I'm just not gonna do that. I could and not use this, that would work. But if I use address, I mean, I could hack my way around this. Just to quickly show you how that would differ then. Now if I have Borscht serialize and deserialize, I could, instead of this, do mood state, create myself a mood account. So that's my account state, and set the discriminator that I want and the mood that I want and the authority. And yeah, here again, that's a hacky situation because it doesn't like my address, but I'm just gonna do this. Oh, sorry, my bad. There we go. And then from that account state, I could say serialize into the data. Yeah. Okay, I don't know how to get to a writer. I mean, okay, that's ugly as fuck, and I don't even know if that works. Let's check. Yes. And we also learned that Borscht does serialize options with a 1 byte, which makes way more sense than how I did it. They're not wasting 3 bytes. So we could say 35 instead, and my native implementation would change that here as well to 3. So that would then be equivalent. Just now we're doing it with Borscht, which, if we check the account, there we go. That's how it looks like now. Fewer bytes. Great. So using Borscht to serialize this into this data here might be cleaner than doing it manually like this. On the other hand, this is very hacky and I don't really like it. So you're probably not supposed to use Borscht in Pinocchio. And I will make a video about proper serialization libraries. I wanted to talk about Win code for a while, so here's that. Because Borscht maybe not ideal, because I would like to use an address here. So that's how we would do it with Borscht. That's how you would do it manually. And that's just the initialize. Let's implement the get, because that's gonna be straightforward. I don't even need the instruction data. We just log the mood is, plus I can't be bothered to put it as a return value because I would need to change that. Which I leave it as homework for you if it's important for you. How can we do return values with Pinocchio? Maybe I'll do a deep dive on that at some point. So let's talk about the mood. I would say we do the exact same thing as we did here. Just have a bunch of moods like these, and then we can get the mood from our mood account, try borrow, and we know that the mood, wait, let's do it in 2 steps. First get the data and then get the mood from the data, and we know it's at location 1. For the byte number 2 is the mood because that's how we defined it here. And then we can make an actual mood from a U8. There you go. And if mood is sum, we print this. Guess I need the message. I am bored. Nailed it. Okay, good. Wrote myself a quick little toString function that takes care of that for me. Let's just quickly see if that would also work. If I add an instruction to get the mood, so a get mood instruction with the same accounts except with this one, and we do 3 for get mood, then we build and deploy, and we call this confirmed. Let's check. And we do see the mood is sad because 0 is still sad. If it's uninitialized or if it just got initialized, then that account is still sad. So let's set it. Let's also implement the functionality for setting the mood. And now here we need to be a little careful because again, we're not in Anchor. We will once again need to have the authority account, and this time, and this is something that you might forget, you will need to make sure that the authority account is actually a signer, because if not, you will want to return an error. I would say invalid argument. So this is a signer check. We as the developers of this program need to make sure that the account that's coming in here actually was signed for, whether that's with a key pair or through a CPI with a PDA, we don't mind, but it must be a signer. Also, we should probably do an owner check that we actually own this account, but hey, otherwise we won't be able to write to it anyway, so it will fail later anyway, whatever. This one, it's a good one. Anchor did that for us because we say signer here. But if we write the program manually like we're doing now, then we need to manually add this. And then we gotta check if, so now let's get the data. Might as well get it mutably right away. And if data 2, so that's the option, so has authority, that's this byte. If it has an authority, then again, I'm doing this manually. I'm gonna say incorrect authority. If that doesn't match, I guess we'll see if that works. I gotta test that. And only if it works, if it has the correct authority, then I'll write to, wait, where am I writing to? To the mood, what we take from instruction data, byte number 2. Oh, again, I didn't make this mutable. So here the instruction data, we once again say it has to have some more bytes. So maybe I also check that before. There we go. Something like that. Not the cleanest implementation, but I guess that should work. So let's add an instruction for set mood. We do number 2. We provide this account and then also my key pair as a signer. And I write 1 to say that I am happy with this account. Let's see. Nope, that didn't work. Hold on. This instruction should also go into my transaction. Otherwise, that's not working. Try again. There we go. And now we can check this account with Solana account. And we will see, there we go. 1 for the discriminator, 1 for the mood happy, 1 for authorities present. And that's the authority. Cool. So that worked. Just to see if I would provide anything else here, another account, then it should complain, yeah, incorrect authority provided. Good. So that also seems to work. Perfect. I think I'm happy with that. Look at this. We can create a new account that we initialize with our program, where we set the mood with our program, and then we get the mood, and the mood is happy. Now, admittedly, working with Pinocchio is a bit more exhausting than it is with Anchor. Also, this stuff is pretty ugly. I'm not super happy with this program, honestly, but it works. It does what it's supposed to do. But you know what? I will give you an implementation that we actually use a mood account and not just the data directly. We shouldn't use Borscht with Pinocchio anyway, because Borscht is not super efficient. That's why Pinocchio doesn't like it. It would allow us to work with variable things, but let's just get rid of it and implement it ourselves. And to make it easy for us, let's just work with a fixed size account. We don't have any variable length stuff in here anyway, so it's gonna be fine. The only thing that is not trivial is this option here. So I'm gonna split this up to a has authority, which is gonna be just a U8. I can't do anything smaller than a byte anyway, for whether or not the option is present. So 1, we have an authority, and 0, we have no authority. And then I'd use the address for the authority. I could pack this more efficient by just using the authority and just the address. And if the address is all zeros, then it represents that there is no authority. So I would just check for that. That's one way how we could do that. But in our example, we always use this additional byte. So let's keep this byte for the has authority. If we wanted to pack efficiently, we could get rid of that. But that's your choice as the developer, how you serialize and deserialize your account. Okay, and now I'm just gonna implement packing. I have two possibilities now. I could either work just with pointers and convert that to an array of 32 bytes again, or I keep it like this and implement the packing and unpacking myself. I think that's what I'm gonna do. We're gonna implement for the mood account. First of all, if it's constant length, good practice is to give it a length, which will be a usize, and it's 1 plus 1 plus 32. So that's 3 plus 32, which is 35. And then I implement the serialization and the deserialization, and commonly you would call this packing. So we implement a pack that takes the mood account and will pack it into some data, which is a mutable slice of U8s. And then the opposite will be I unpack from the data, which here is just going to be a slice of U8, doesn't need to be mutable. And this will return a self like this. And then we just quickly implement this. So this is basically what we're doing here now, this thing. So I'll copy that in there. And instead of the 1, I say self discriminator. And instead of this one, I say self has authority. And then we're missing the data 1, which was the mood. And here I also get that from the self authority, which is an address, and copy the bytes into here. So that's the packing. And then the unpacking is the other way around. We have the data and we want to create a self. So we create a self with those where the discriminator is the data 0, the mood is the data 1, data 2. And here we need to create an authority. So far we've just compared the bytes. Now we will actually get an actual address new from array. That sounds about right. That takes a uint8 array, perfect. And then we have to try into, because it's not guaranteed that's actually 32 bytes, but I know that it's 32 bytes, so there you go. So we have the pack and unpack implemented. Now we can also use that such that we actually use the mood account for once. So basically, instead of that, we create ourselves a mood account, except now I have to split this option out. I need to say has authority is 1. There's no possibility in this case to not have an authority anyway. And this one is the actual address. Not super efficient because I'll have to clone this, which is not ideal, but whatever. And now I can account state pack this into the data, and that should then write this account state into the actual mood account. And then when we use the mood account, instead of working with the data directly, we can get, I'll call it mood data, mood account, unpack this data, and then I get a mood account from this. And here, and now basically replace this with a mood data has authority. So this now converts this byte to a bool that we can use it. And then here, when we compare the account address, I don't need to go through bytes. I can compare the mood data authority directly. However, now we also still want to write. So what I would do is mood data mood, set this to the new mood. Therefore, I will also need to make this mutable. But then this, of course, is not yet persisted to the actual account. So I would need to do the same thing as before as well. So now basically I need to write it back. However, that is a bit inefficient because we would really just need to write 1 byte, this one. And now we're writing back the entire thing if we use the pack and unpack. So yeah, that's a bit inefficient. However, it will work. Let's first just check out that this will actually work. Let me add a message. Mood account initialized, just so we know we're in this version. And we deploy this program. And then we call this program and check this account. And we'll see 35 bytes. And it's packed the same way as before, even with this version of the program. So this also works. Now we're actually using this mood account, but as I said, it's a bit inefficient. So the other way how I can do this is just using pointers directly. Also gonna show you that while I show you stuff. So instead of implementing the packing and unpacking, I can just say this thing here is just a U8 array. Really, it's an address. And then I'll just work with pointers, which is not great, but it will work. So I get a mood data pointer from the data. For this to work reliably, we need to say represent C such that it has a constant pointer layout. Otherwise, this will result in weird behavior that we don't want. And then we can just work with a pointer as a mutable pointer to a mood account. And now we can do this again, but we can directly work with, instead of the data 0, we say mood data. There we go. However, dereferencing a raw pointer is unsafe. So this is the efficient way of doing it, but obviously you need to know what you're doing. And Rust is like, this is unsafe. I want you to know that this is unsafe. But I'm like, okay, fine. I agree that this is unsafe and I'm okay with this. And then I can directly work with it like this. So this is the mood data has authority, and this is the mood data authority. So now we're using those fields directly from here because we just cast the pointer, which again, unsafe, not super clean, but internally it will do the same thing as we did earlier, just that now we don't need to remember, oh, discriminator, was it 0, has authority, was it 1? It's just nicer to write it like this. And then also down here, if we do the same thing, instead of the unpacking, just casting this pointer, then we can do the same things as before, except here we now need to compare bytes from the address again. And then we don't need to pack, because if I now say mood data mood, then it will still write this directly because it's now just a pointer there. So this should still work. There we go, same result, also with this, and also here. Even with using a raw pointer, the mood in the end is happy. So that worked. Again, maybe this solution is not for how to get started with Solana development, but I wanted to show it to you anyway, just what the possibilities are if you don't use a library to deserialize, but do it yourself. Okay, that was just a quick excursion because I didn't want to leave you without that. But the gist of it really is just you have to define what your account layout is, and then you gotta stick to it, basically. Oh, and also, when you're doing this, maybe it would be a good idea to keep the length here and do a check that the data of this account is at least the mood account length. And if it's not, we return some error like invalid account data. That would be good to be added before we do an unsafe cast like this. Yeah. Because again, if you don't use Anchor, who does it all for you, then you gotta do those checks yourself. And maybe also the same down here. Yeah, that's that. And the real important thing for me was just for you to get a better understanding of how accounts are being serialized and then deserialized. So to wrap this up, let's deserialize such an account. Because we know how it is being serialized through our program. We have that kind of state here. That's usually what you find in the state.rs file. If you ever look at examples, you'll find that in the state usually. I just put it all in my lib file because I'm a lazy dev. So we want to deserialize this account. Anchor also does that automatically for us, but we're not using Anchor. We don't even have an IDL. So for instance, let's take this account. This is our mood account, and we will do something similar than what we did earlier. So first of all, we're going to use the RPC to get the raw data. So we get account info for this mood account, send this, await this, and then the account info in value will have date, except I probably want a diff base 64 encoding, then I have base 64 encoded data here. And here comes one of the weirdest things about the kit. We get a base 64 codec, and now usually you would from the base 64 decode to get the data, but it is encode because we want to stay consistent, and encode always takes the high level thing and creates a U8 array from it. So if you want the actual bytes from that base64 string, then we gotta actually encode this to data, which will then be a int8 array. That's a bit weird, but you'll get used to it if you work with a kid. And now we just need to build something similar that we have here, where we say discriminator, mood, and optional authority. So we build ourselves a codec. Let's say it's the mood account codec that has the discriminator, the mood, and the authority. This one is a U8, this one is a U8, and this one is a option codec with an address inside. So that's how we would build a codec that can de and encode this mood account. So the decoded mood account, we use that codec to decode the data, and then we have in this decoded mood account the mood, discriminator, and authority. The discriminator I'm not too interested in, but the mood is interesting, and I could also match that to the corresponding type, one being happy or whatever, and the authority would be authority. I could say if we have an authority, then we print the authority, otherwise no authority. And then here it will actually let me access the value for the authority if I checked for some. Yeah, and if we run that, deserialize account, let's go. Then we see the mood is 1, it's happy, and that's the authority. So that is how we would now on client side deserialize the account. Because we have the data, the serialized data, which is just some bytes. And then to get our information again, we need to deserialize it in the correct way. Okay, good. I hope that after today's video that you understand what serialization and deserialization is and how we do it with the kit and in Solana programs, and also why it is so important for Solana programs, because both for instruction data and account data, we as the developers are responsible to say in which order the bytes need to be provided and what they represent, because they are just bytes, they can represent anything. The program needs to interpret that correctly, and so it's your job as the developer to take care of that. As a homework, just play around with it, maybe write your own little Pinocchio program or Solana Rust program if you want to. Really, I want you to understand how deserialization works. So if you want a challenge, try to manually deserialize an account of a program. Maybe a simple one like mine, or a more complex one like a token mint or a token account. For that, you will need to know how those accounts look like, but we said we can find that in the state of the implementation. So for instance, a mint account would look like this. Here we have a C option. What does that mean? We already hinted at that earlier. Or a token account would look like this. So create yourself a token account and try to manually deserialize an account knowing that those are the fields of it. That's always a good exercise to do. So that's why I give you this as homework, because I want you to understand what accounts look like, what's really written inside the account, because otherwise it's just bytes. So yeah, that's the homework. Is it clear? I want you to build such a thing for a token account or token mint, and then actually create a mint and deserialize it just to check that you get the right things back. Okay, good. That was day 6 already. We only have one more day tomorrow where we're gonna wrap it all up and see where we can go from here. Because obviously I did not cover all the topics that are relevant. We didn't talk about local testing yet. We didn't talk about surf pool. We didn't talk about SIMDs. We didn't talk about so many things. So come back tomorrow for one last time this week, and I'll walk you through the next steps now that you have the basics where you can go from here to become a real Solana dev. So see you tomorrow for day 7. You'll find that one here. Like this one, subscribe if you haven't already, and I'll see you tomorrow. Don't forget your homework.